Now, to apply the continuity equation and Bernoulli's equation of various heads, we will deal today in what is known as the Torricelli's law, the speed of efflux and Venturi meter, plus other things. Now, to explain it out to you, first of all, I will explain the word efflux. Efflux means fluid output. Okay? And here I have a container which is filled with a liquid of density rho, and this is protected from the atmosphere. So the liquid right now is at the level Y2 above the reference point, and it has got a nozzle kind of a structure here from which the efflux will take place, and we will talk about the velocity or speed of efflux. Because it is exposed to the atmosphere, so the pressure over here is the atmospheric pressure, and the pressure here, over here, P2, we write as simply P. The area of cross section of this container is A2, which is much higher as compared to the area of cross section A1 over here. The velocity of efflux, the speed of efflux is taken as V1. So with this build up, where this is not exposed to the atmospheric pressure, I have taken two surfaces, surface 2 and surface 1. So surface 2 level is Y2 and surface 1 level is Y1, and the level difference, spelling mistake, difference, okay, level difference is equal to H. Here I have shown you like H, which is Y2 minus Y1. As I said, the pressure at 2 is P and the pressure at 1 is the atmospheric pressure PA. The area of cross section I have written here at level 2 is A2, and the area of cross section at 1 is A1. And as is evident from here, A2 is far larger as compared to A1. Velocity at this level, the velocity of the fluid at this level is taken as V2, and the velocity at 1 is taken as V1. Now we write the continuity equation, and the continuity equation is musically A1 V1 is equal to A2 V2 is equal to AN VN is equal to AV is equal to constant. So from this equation I can calculate the velocity V2 over here as A1 divided by A2 multiplied by V1. Okay. Now this is true. Even if we take as A2 is greater than much greater than A1, we may take V2 is equal to 0. Okay. And this is for the consumption of Bernoulli's equation. If I write the Bernoulli's equation at level 1, level 2 respectively, I find that the pressure is PA plus half rho V1 square plus rho GY1 is equal to P, the pressure over here at level 2, plus half rho V2 square, which is taken as equal to 0, because the velocity V2 has been taken as equal to 0, plus rho GY2. Okay. So I can rearrange the terms and write this half rho V1 square as equal to P minus PA, the difference in the pressure, plus rho G Y2 minus Y1, which I can write as, again I am taking this equation, I rearrange the things, I multiply by 2 and divide by rho, so I get V1 square is equal to 2P minus PA divided by rho plus 2G Y2 minus Y1, and that is 2GH. Okay. So finally I arrive at an equation of this kind. An equation of this kind. Okay. V1 is equal to 2 GH plus 2 P minus PA into rho. Okay. Now let us try to see and to listen to this equation, because this equation speaks. The equation speaks in that if in the first case, if P minus PA is very large as compared to this term is very large as compared to the other term, then what we find is that V1 turns out to be equal to, V1 is equal to under root of P minus PA into 2, into 2 here divided by rho. Okay, plus negligibly small 2gh, negligibly small 2gh, and if the pressure difference over here and this term is the dominating term, we can neglect this term. Okay, and this is exactly what serves the case of jets. Okay, jets where the pressure difference is too large, so this 2gh has no significance at all, and we are left with the velocity as equal to 2. So velocity 1 can be written in that case as 2 upon rho into the pressure difference P minus PA. This is the approximation that helps us in the case of such machines as jets. Okay. Then it may happen that I may do away with the enclosure part here, and then this P2 also becomes equal to PA. Okay, P2 becomes equal to PA. So in this equation, P minus PA is equal to PA minus PA, and this term goes, and we get the equation V1 is equal to under root 2GH, under root 2GH. Okay, so let's see if you can recall anything about under root 2GH. Under root 2GH, friends, is something that you know from before, we know from before, that if a body is falling freely under gravity, if a body is falling freely under gravity from this level down to another point where the height difference is h. Okay, so here if I take the velocity equal to 0 and we drop the body from here under the influence of acceleration due to gravity which is working in the downward direction, then we find that the velocity over here will be equal to and we can equate, we can apply the principle of conservation of energy. Then I can say half, here the velocity v is equal to v, so half m v square is equal to m g h. Okay, that is the principle of delta kinetic energy. Delta K is equal to delta U. The difference in the kinetic energy of the two levels is equal to the difference in potential energy of the two levels by virtue of the difference of position. So M and M, they cancel out, and I find that V square is equal to 2GH. So it's interesting, which gives us the value of the velocity is equal to under root 2GH, okay, which is the same over here as has been obtained in the case of efflux. So in the case of efflux, if the height difference is h, then the velocity of efflux turns out to be the same as if there were free fall under gravity. Okay, so this is this one, V1 is equal to 2GH plus 2 P minus P8 pressure difference divided by the density. This is basically what we call the Torricelli's law, and we have been able to obtain the speed of efflux over here. Okay, so I hope that I have been able to tell you that and emphasize that in case the two pressures are the same and there is a difference in the height h, then and so we can say that if there is one height h1, another height h2, so we can write that this v1 upon v1 prime, let us say that this is h upon h prime, and naturally we obtain a relation like that from here or v1 upon v2 is equal to h1 upon h2 kind of equation, whatever way you want to remember, it's up to you. Okay, so now we deal in Venturi meter. A Venturi meter which measures the flow speed of incompressible fluids. Okay, these are some of the conditions. Most of the fluids are incompressible, including water, and it is based on the principle that we have a pipe, and then here there is a constriction, meaning thereby that the cross section is reduced drastically. When the cross section is reduced drastically, I have just shown you the lines of flow, and here I have not done anything because of the space and my drawing is not so good. So we find that the fluid goes as it comes over here. There are 2 points under consideration, point number 1 and point number 2. At the point number 1, the area of cross section is capital A, and the point number 2, the area of cross section is small a. Okay, the velocity here is v1, the velocity here is v2. Okay, of course the pressure over here is p1 and the pressure that develops over here is p2. So this is a very simple arrangement, but there is an attached manometer. Okay, you can see that the level over here is the same. Okay, here and here the level is the same, so that there is no level difference, and therefore in the Bernoulli's theorem, in the Bernoulli's equation, we will not deal in the potential energy variations. So the potential energy variations will be done away with. Of course, it functions on the simple equation of continuity. which says that AV is equal to constant. The beauty of the equation is AV is equal to constant. So I can write that A1 V1 is equal to small a V2, which gives the value of V2 as equal to A2 upon A1 into V1. So because capital A upon A, but capital A is very, very large as compared to small a, and therefore this quantity becomes very high, very large. Okay, so that means the velocity over here, the velocity with which the fluid fluxes out from here, it becomes quite large. Okay, so now the next, after that we make the application of the Bernoulli's equation, and the Bernoulli's equation will say that the pressure plus the kinetic energy plus the difference in the potential energy over here, is equal to pressure plus kinetic energy plus the potential energy. The two potential energies are equal, therefore we are not considering over here. So I can write P1 plus half rho V1 square from the Bernoulli's equation as P2 plus half rho V1 square A upon A, substituting value of V2 as V1 into A upon A, this whole square. So therefore I can now write the equation P1 minus P2 is equal to this. Rearranging the terms, there is nothing very special about it. So half rho V1 square I have taken as common, so this becomes equal to A upon A whole square minus 1, no problem. Now this manometer has a liquid of density rho m in it, and the pressure difference at the points 1 and 2 can be measured with the help of this manometer, and we can see that the pressure over here becomes larger as compared to the pressure over here. So I can write that P1 minus P2, okay, the pressure that we have, this is rho mgh, okay, where rho m is the density of the manometer liquid. Okay, it can be mercury or it can be any other liquid. It all depends upon the ease of application. So P1 minus P2 is equal to rho mgh, and I can substitute, therefore rho mgh will become equal to this quantity which I have written over here. Okay, if I rearrange the terms, then V1 becomes equal to, okay, I multiply by 2 and divide by rho. So what I get is this one, okay, 2 rho mgh upon rho into a square, a minus a square, a divided by a whole square minus 1. Okay, now like I said, this equation may also speak. Okay, this equation may also speak. The equations do speak. For example, there is very simple thing about this equation is that suppose this capital A is very, very large as compared to small a, then capital A upon small a whole square becomes very, very large as compared to 1, and we can ignore the value of 1 and obtain the relation as 2 rho m g h small a square upon rho capital A square, etc. So this is the physics behind the Venturi meter, and there are many applications, including that of deodorant bottles, and of course the same principle is applied in the blood flow in arteries, blocking of arteries, etc., and pichkari, and the pump that is used at the car service stations to have a jet off. So a jetting is actually even with the same principle, and of course these are the applications that we can talk about. But I would suggest that instead of me going into the details of those applications, I will expect you rather to go through all those things, their tidbits, and try to understand what are the things, because there is not much principle involved. Okay, all the principles which are involved over there I have already told you about, and therefore what we have done today, explained you the Torricelli's law, speed of efflux, and the physics behind the Venturi meter, which is also the physics of many a thing and many applications there, including the problem of heart failure, blood flow, etc., etc. I'll just enumerate those things here. So, as I told you, these principles that we have used in Venturi meter, the Torricelli's law, etc., and Bernoulli's principle, etc., etc., they are used normally in what I am not going to take up, but instead asking you to read all by yourself carefully, is, for example, in spray gun. This is what we know, and we use it during the festival of Holi. What is the pitchkari? Pitchkari. And children used to vie for a pitchkari in my childhood days. So, spray gun, pitchkari kind of thing. And similarly, in the carburetor of automobiles, the nozzle is using the same kind of a principle, where the velocity of the fluid is increased because of the constriction. Okay, filter pumps and aspirators, atomizers and sprayers. Okay, these are some of the topics. The blood flow in normal arteries and in choked arteries, which may result in a heart attack. That you must read carefully this time. And then with the same set of principles, we can explain the dynamic lift or the aero lift, etc., etc. Where there is physics of the spinning ball, there is physics of a ball which is non-spinning, okay, and how the pressure difference at the wings of an aircraft can make it lift. Even if the pressure difference is about 6 to 8%, there is an uplift and the aircraft goes up and as per the design. So, I have enjoyed this part and explained to you, but all along what we have done is that the liquids have been taken as incompressible, and we have explained that there is hardly any loss of energy. So when the liquid gushes out of a system in turbulence or otherwise, then there is no sound, no heat is generated, which is not true. In actuality, we do have losses, and those losses are because the resistance between the different layers of liquid, when they are, even if they are moving in the same direction. We'll talk about that. What I mean is viscosity. Okay, in the next lecture, and thereafter we take up the surface tension. So, Thank you very much.